Good morning YouTube, and welcome to today's video where I'm going to be answering an electrode potential question, and I've brought back some of my top tip flashcards from the 5 top tips video I did on electrode potentials recently, which you may wish to give a watch before you carry on watching this video, but I'm going to bring these in at relevant points when I am answering this question here, because my 5 top tips, of which 2 of them are not relevant for this particular question, but my 5 top tips tried to cover some of the fundamental things that we would need to be able to do to answer the majority of the electrode potential questions. And in this particular question, we're being asked about the reducing agent, the weakest one from the table, and we're being asked to calculate the EMF of a particular cell. We are also being asked to suggest a possible equation for the overall reaction between the 2 half cells, and they are 2 really fundamental skills. So I'm going to bring those top tips back in as they are relevant, but if you wish to watch that video first, you will find it on my channel. So we don't need the top tips for part A of this question, because we're being asked to deduce the oxidation state of nitrogen in these 2 different species here. So what you can see that I've done in the pink is I've annotated for each thing the oxidation state that we know for the oxygen, which is -2, and then in the NO3 minus ion there are 3 of those oxygens, so we've got 3 lots of -2 there. And then I've written what the overall oxidation state on the compound or the ion needs to be. So compounds need to have no overall oxidation state, and thus if we know the oxygen has an oxidation state of -2, X, which is the algebraic letter I've used to represent the oxidation state of nitrogen, X has to therefore be +2, because +2 minus 2 is the only way to get 0. So in NO, N's oxidation state is +2. When we have ions, the overall oxidation state equals the charge on the ion. So rather than equaling 0, here it needs to equal -1. So X again, which I've used to represent the oxidation state of the nitrogen, X, 3 lots of -2 for the oxygens, needs to go to -1 overall. That means that X has to be +5, and thus in NO3 minus, the oxidation state on the nitrogen is +5. So moving on to part B, we're asked to state the weakest reducing agent in the table, and this comes up time and time again with these sorts of questions. So in my top tips video, tip 5 related to oxidizing and reducing agents, and I said that we should always refer back to the definition for either oxidizing or reducing agent, and that we needed to then be really careful to make sure that we gave the species that appeared on the correct side of the equation, which again links back to the definitions. So we've been asked in our question for the weakest reducing agent. So first of all, referring back to the definition, a reducing agent will reduce something else in the equation, and in the process is itself oxidized. So when we're then thinking about which side of the equation we want to choose a species from, if everything with regards to the half equations on the electrochemical series is written as reduction, the thing that would be undergoing oxidation will always be the thing that's on the right hand side. So we're looking in our table for anything that appears after the arrows, because oxidation in all of these equations is represented from the right hand side going towards the left. Now if we want the weakest reducing agent, we want the thing that really actually does not want to be oxidized. If we were looking for the best reducing agent or the strongest reducing agent, we'd be looking for the thing that really does want to be oxidized. So this then requires us to know another thing, which is what these different values in the table actually tell us. So positive values tell us that the half cell wants to undergo reduction, whereas negative values tell us that the half cell actually wants to undergo oxidation. So if we want to find the thing that really doesn't want to be oxidized, we want to find the half cell where it most wants to undergo reduction, which is the one with the most positive E0 value. Out of all the ones listed here, this is the one that wants to undergo reduction the most, because its value is the most positive. So if we're then trying to find the worst or the weakest reducing agent, the thing that really does not want to be oxidized, that would be the Cl- ions. They really don't want to be oxidized because actually the chlorine atoms really want to be reduced and gain these electrons to become ions. And that does make a bit of sense when we think about it logically. Chloride ions that are stable with their noble gas electron configurations aren't going to want to lose electrons and turn back into atoms again. So that's not likely to happen, which makes that the weakest reducing agent here. And finally on to part C, where there's quite a lot for us to do in this question. So first of all, we have to use the data from the table to identify an acid that will oxidize copper and explain our choice of acid. Now this links in with tip 2 from my previous 5 top tips video, which is linked to how we go about setting up the cell. So we need to understand which half cell is going to go on the left hand side and which is going to go on the right hand side, and it's always oxidation that occurs on the left hand side, and in our question we are wanting to oxidize the copper, and it is always the more negative E0 value. Now if the values are not negative, it will be the less positive one that would undergo oxidation. So looking at my table and finding the half cell where copper is being oxidized, i.e. the copper needs to be on the right hand side, and the equation is going to go from right to left. The value for the standard electrode potential is 0.34 volts. So I wrote the O to represent that this needs to undergo oxidation, so we cannot therefore have any of these half cells involved because they are either less positive, 0, or negative, and all of these three would preferentially undergo oxidation, meaning that the copper then would not be oxidized. So we cannot use any of those. So that left me with the 3 at the top here to pick from. Now the only one that can act as an acid, because it has a source of H+, is this half cell here. So the acid that we are going to use is nitric acid, so the H's and the NO3 to make HNO3. And when we're explaining why we're going to use nitric acid, we would say that the standard electrode potential value for this half cell is greater than or more positive than the standard electrode potential value for the copper one. More positive values show that they want to undergo reduction. So that means if these were the two that we were pairing together, the less positive one would be the one that was undergoing the oxidation, which is what we want to happen because we want to oxidize the copper. Now in terms of how we would write out that explanation, mark schemes often write it in this particular form here. So where the standard electrode potential value of the half cell between the NO3- and the NO is bigger than the standard electrode potential for the copper 2+ and the copper half cell, and that basically means, as you can see here, that the reduction half cell has a more positive value than the oxidation half cell. Now sometimes, and interestingly not on the mark scheme for this question, you can use EMF as an argument, and I think possibly the reason why you can't here is because part of the question is asking us to calculate the EMF of this cell. But if you are not asked to do that, another way you can explain why you've chosen nitric acid here is calculate the EMF of the cell and prove that the reaction is feasible. Now there's only actually one other acid in the table that we could have used, which is this half cell here, where we've got H+ ions and SO4 2-, so this would be sulfuric acid. Now, as I said before, because this value is less positive, this would then preferentially undergo oxidation, which is not what we would want. And again, we could prove that using the EMF. We would get a negative value for the EMF, which would show that that reaction is not feasible. But in this case, we couldn't do that, I think, because we're being asked to calculate the EMF of the cell as part of the question. So you want to be writing it something along the lines of this. So the standard electrode potential value of the half cell undergoing reduction is more positive or greater than the standard electrode potential for the copper half cell, which we want to undergo oxidation. And then the next part of the question says that we need to use these data to suggest a possible equation for the reaction. And again, this links into the 5 top tips video that I've done previously, which is writing the overall cell reaction equations, i.e. can you write a redox equation? Because within the cell that we have just set up, we have the copper being oxidised and the nitric acid undergoing reduction. And if we've got oxidation in one half cell and reduction in the other, we've got redox overall. So the tips that I gave were to reverse the half cell that's undergoing oxidation, multiply the equations accordingly to balance the electrons, and then combine them together and, where necessary, simplify the equations down. So you might have already spotted that in the table where I wrote the O for oxidation for the copper half cell, I also did a backwards arrow to show that this reaction is occurring from right to left. Now that might be sufficient for you to remember that oxidation is from right to left, but I personally need to write out the equation again the right way round. So the copper being oxidised to form copper ions and releasing 2 electrons. And then I've also, in this space here, rewritten out the reduction half equation as well. And then in order to balance my electrons, I've got 2 electrons being lost during oxidation and 3 being needed to be gained. So in order to get these to balance, I'm going to have to use the lowest common multiple, which is 6. So times the top equation by 3 and the bottom equation by 2, and then combine them together. And it turned out that nothing could be simplified in this particular instance because I didn't have anything that was the same on both sides, other than the electrons, which cancel, so should not be included in the redox equation. But there was no H pluses on both sides, there was no water on both sides, so once I'd combined them together, that was then my final answer. And then the final thing we're asked to do is calculate the EMF of the cell that has that reaction. So to calculate EMF, we use the standard electrode potential for the right hand side minus the left hand side. So the right hand side is where reduction occurs and the left hand side is where oxidation occurs. So we're going to do positive 0.96 take away positive 0.34, which I think gives me a value of 0.62 volts. That's positive. That means that the redox reaction will be occurring as we have set it up here in this question. Now, I hope that that's been useful. There are lots of questions that are similar to this that use these fundamental principles. So if you are struggling with electrode potentials, you may wish to go back and watch my top tips video from previously. But if you still have questions, please let me know and I can think about what future video, follow-up video I can do to support you. Take care everyone. Thank you for watching.